Okay, welcome everyone. Today we're talking about master theorem for solving recurrence relations. It's an excellent cookbook method. So let's dive right into it. Everything we're covering here today is there in the textbooks as well under the chapter of divide and conquer. So you should be able to find it there as well. Okay. So let's see. So master theorem for solving recurrence relations. It's an excellent cookbook method, but it only applies to recurrence relations of the following type. T of n is equal to a t n by b plus f of n, where a and b can be some constants, and f of n is some other polynomial term. So essentially, we are saying that t of n is equal to a t n by b plus n power c. So in this case, master theorem will not apply to recurrence relation of this type. S of n is equal to s of n by 2 plus s of n by 3 plus f of n. Okay. And the master theorem has three cases. What we're always doing is we're always comparing the f of n term, which we call the merged term, with the recursive term here, which is n powered log of a to the base b. So essentially, we take log of a to the base b and compare that with this polynomial, the exponent here, which is c. So the first case says that if log of a to the base b is greater than c, then we simply write down t of n is equal to theta of n power log of a to the base b. And in this case, we call that the recursive part dominates. Case 2 is that those two terms are equal. That means log of a to the base b is equal to c, in which case we write down t of n is equal to n power c times log n. And in case 3, we say that c is actually greater than log of a to the base b, in which case we simply just write down t of n is equal to theta of f of n. In this case, we say the merged part dominates. Again, the first part dominates, or it's equal, that's case 2, or f of n dominates, that's a case 3. That's simply master theorem, okay? There is a slightly more general formulation of master theorem, which you see on this slide here, which looks very similar. But here, if you observe carefully, f of n is allowed to have a polynomial term, also a log term, okay? So here's n power c log power k to the n, which means log n times log n times log n up to k times. And if k is 0, that means essentially you have the previous formulation as n power c. So t of n is equal to a t n by b plus n power c log k n. And it still does not apply to s of n is equal to s of n by 2 plus s of n by 3. But we are allowing at least a log term in the f of n. The three terms are still the same. The three cases are still the same. We just make the small adjustment here for this log term here. Again, if the case 1, that means this term dominates. If log of a to the base b is greater than c, it's still case 1, and the answer is still n powered log of a to the base b. If c is equal to log of a to the base b, then it becomes this term's time log n, which essentially can be written as n power c log of k plus 1 to the n. And if the merged part dominates, that means c is greater than log of a to the base b, then just whatever is on the right-hand side, you will write it. So essentially, the log term here does not play any role in deciding whether it's case 1, case 2, or case 3. But if it is case 2 or case 3, then we do take into account when writing down the final answer. Does not determine the case, but can affect the final answer, okay? So for case 1, case 2, case 3, you're still comparing the same exact that you're doing in the previous version there, okay? So what's the intuition of master theorem? We won't prove it, but let's make some couple of observations here. Let's suppose we just write down master theorem as t of n is equal to a t of n by b plus f of n, and we were to simply unfold it. So we would say that t of n by b is equal to a t n by b squared plus f of n by b, essentially just replacing n with n by b everywhere here. And then plugging that in, we will get t of n is equal to a squared, t of n by b squared, plus a times f of n by b plus f of n. And we keep doing this thing. We will get T of n is equal to a power k, T of n by b power k, plus f of n plus a times f of n by b, etc., etc. Now we cannot simplify the right-hand side terms because those belong to f of n, but we can remove t from the right-hand side by simply choosing the value of k here as something that's log of n to the base b, in which case we will receive that T of n is equal to a power log of n to the base b plus all these f terms, and this can then be rewritten as n power log of a to the base b plus f of n terms. Again, we cannot simplify the right-hand side, the f of n, any further without knowing what f of n is. So essentially here we can make the observation that if f of n is small, we may have to quantify it, how small, but at a certain level of f of n, this term will dominate, and then the first term will dominate. If f of n is very large, f of n will dominate, and if they're equal, then it can be considered that there are log of n terms here. Then we will have to take the f of n multiply with log of n. Again, it's not a full proof, but hopefully the intuition is clear on why are we even comparing c with log of a to the base b. Where does the log of a to the base b comes from? That at least we have shown here in terms of unfolding and how that term comes to be. So let's see some examples here. Okay, so let's dive right into it in terms of examples, because that's how we learn about master theorem. So let's take this example here where a and b are 2. So let's play with this variation here a little bit. T of n is equal to 2tn by 2 plus log n. So a is equal to 2, b is equal to 2, c is equal to 0. As you can see, n power 0, that's 1. And k is equal to 1 because it's log n. If it was log square n, that means log n, that would be k equal to 2. So our very first job when we see a recurrence relation is to simply write down these 4 things. A is equal to this, b is equal to this, c is equal to this, k is equal to that. Okay, that's our very first chance. Then after that, we simply compare what's log of a to the base b and see how it compares to c. Now k will not play any role in making this comparison here, but here we'll write down for this specific case here that log of a to the base b is equal to log of 2 to the base 2, which is equal to 1, which is greater than c because here c is 0. Therefore, we call it case 1. That's case 1 of master theorem, in which case the answer will just become T of n is equal to theta of n powered log of a to the base b. That's just theta of n. Okay. Now, in this case, we went through a little bit of work here to get to the answer, but finally, by the time we learn all these examples, we can just simply inspect it and simply write down the answer. So that's our level of comfort usually that we have with master theorem. Let's take another example. Looks similar, but I've changed it a little bit. This is example 1b. Here, f of n is equal to n. Now, c is equal to 1. This is n power 1. K is equal to 0. There are no log terms here in the f of n part. Log of a to the base b is equal to 1. That's equal to c. Therefore, that's case 2. Case 2 is when they're equal. So therefore, by master theorem, we'll simply take f of n times log n, which is equal to n log n. This, I'm sure you also observe, is also the time complexity for the merge sort and many other similar algorithms as well. But for the merge sort, we will have n log n, which is exactly what the master theorem shows as well. Let's take another example. Again, we have changed it a little bit. 1c here is saying T of n is equal to 2tn by 2 plus n square. A is equal to 2, b is equal to 2, c is equal to 2, k is equal to 0. No log term here. Log of a to the base b is equal to 1, which is less than c. So we call it case 3. That's equal to theta n squared. Okay. One more here. Now, in this case, f of n is equal to n log square n. So a is equal to 2, b is equal to 2, c is equal to 1, k is equal to 2. So in this case, log of a to the base b is equal to 1 is equal to c. So it's equal. So therefore, we'll have f of n log n, which is n log cube n. So here was log k. Now it becomes log k plus 1. This is also case 2 because A, B, and C told us that it's case 2. Let's change a little bit. A is equal to 3, B is equal to 2 now. So we have this recurrence relation. T of n is equal to 3tn by 2 plus n. A is equal to 3, B is equal to 2, C is equal to 1, no log term. So now we have log of a to the base b is greater than 1. Therefore, it's case 1. Therefore, the answer is n power log of 3 to the base 2. Change it a little bit. Now we have log terms here. C is equal to 1, K is equal to 5. But because K does not play any role in determining whether it's case 1, so it's still case 1. And the answer is still the same. So between the previous one and this one, the answer did not change. Okay. And that's a common occurrence across many applications of recurrence relations, that we change it a little bit. It does not make any difference to the final end result, because one part that was dominating is still dominating. Even if the other part is smaller or larger now, the first part is still dominating. Let's take another example. Now here, T of n is equal to 3tn by 2 plus n square. In this case, A is equal to 3, B is equal to 2, C is equal to 2, K is equal to 0. Log of a to the base b, even though we exactly don't know what log of 3 to the base 2 is, but we know that's less than 2, because log of 4 to the base 2 is 2. So that's case 3, in which case we will have, the answer is theta of f of n, which is theta of n squared. Again, let's shift this a little bit. Now we'll have A is equal to 1, B is equal to 2. So they're all of this form, T of n is equal to T of n by 2 plus something here. So in this example, A, we're saying that A is equal to 1, B is equal to 2, C is equal to 1, K is equal to 5. Log of A to the base B is equal to 0, because A is 1, log of 1 is 0. So that's less than C, therefore that's case 3. Therefore, T of n is equal to theta f of n, which is just whatever we see on the right-hand side. We change this a little bit. Now we don't have the n power 1, rather we have n power 0. So log of a to the base b is equal to log of 1 to the base 2. That's equal to 0. C is equal to 0. Therefore, now it becomes case 2. Because now those terms are equal. So we'll have to now take this term, multiply with log n. So we'll get log 4n. Okay. Let's take some more examples. F of n, now we're going to keep f of n constant and change a and b to see what happens here. This is our example for a here. T of n is equal to 5tn by 2 plus n cubed. So a is equal to 5, b is equal to 2. Sorry, c should be equal to 3 here because the constant is 3. K is equal to 0. So log of a to the base b, which is less than 3. So therefore, it's case 3. The answer is dominated by the merged part, which is n cubed, theta n cubed. Okay. Now let's change a is equal to 7 now. Even if a is equal to 7, still log of 7 to the base 2 is less than 3. Therefore, we still get the answer n cubed. Okay. Now we have a is equal to 8 here. Now in this case, log of 8 to the base 2 is equal to 3. It's equal to c, right? So therefore now we have case 2. Sorry, here c should be equal to 3 as you observe here. This is c equal to 3. Therefore, by Master theorem, T of n is equal to f of n log n, which is n cubed log n, right? And similarly here again, in all these examples, c is equal to 3. But now a is equal to 9. Therefore, log of 9 to the base 2 is greater than 3. Therefore, it's case 1. Okay. So therefore, we have by Master theorem that T of n is equal to theta n power log of 9 to the base 2. So that's basically Master theorem. You can quickly do a little bit of a self-check here. See if these examples make sense to you. Then you're feeling pretty good about Master theorem at this point. Again, when we look at this thing, we can simply just write down the answer. A is equal to 6, B is equal to 2, n cubed. So n cubed term will dominate this. So the answer is n cubed. It's now is equal to 5. b is equal to 2, c is equal to 2. Log of 5 to the base 2 is greater than 2. This term will dominate. That's your answer. Here, similarly, this term will dominate. That's your answer. Here, these terms are this term is larger, so that's your answer. So that's basically master theorem for you. Very, very, very good cookbook method. You look at the recurrence relation, right? You can write down the answer. Only for some forms of recurrence relation, but where it works, it's like magic, right? You can write down the answer very quickly. There are some other cases where even if it has the right format of A and B, still doesn't work, like this example here. So here we have T of n is equal to 4Tn by 2 plus n squared divided by log n. So K is not allowed to be negative. So this is not solved by our version of the master theorem. The right answer is n squared log n, but you would have to compute it separately to confirm that this is not covered by the version of the master theorem that we have covered here. Okay, what we have covered is where we have n power c log kn, but both of those are supposed to be greater than or equal to 0. In this case, it's kind of like negative because log n is getting divided. So it's not handled here. That's pretty much what we have on master theorem. Have fun, keep learning.